Okay, so this is supposedly the most important theorem in topology, although some people think it's the equal second with Urysohn's lemma. We've already done. Okay. So we're quite happy with finite products of compact spaces being compact. And you can even make the proof for countable collections using the same method. And so just remind you how we did it. So we have, say we have an open covering of our product of two compact spaces. We cover it by basis elements. And then the idea is we look at a slice. A slice is going to be homeomorphic to just one of the compact spaces. So it's going to be compact. So it has a finite cover there. And in fact, we have this tube lemma, which says that not only does that finite subcover cover the slice, it actually covers a tube, which is what we, so we actually need some open neighborhood here, and then we have finite number of those neighborhoods going to cover X, and so we get finite collection of finite collection, we get a finite collection. Okay, so that's, so it is possible actually to turn this proof into a proof for arbitrary index sets with the product topology. And to do it, we need the well ordering theorem. So we just well order our index set, and we can use trans-finite induction, which is basically the same as induction. So we call a subset of a well-ordered set inductive if we have, and if a section is in this subset, then the actual, remember this is the element for less than alpha, then that means that alpha is in the set. And so that's exactly what you do in induction, right? You assume it for n or n minus 1, and then you prove it for the next one. And so we get a principle of trans-finite induction. So if you've got a well-ordered set and you've got an inductive subset of J, then actually the whole set is J0. So it's actually true for all J. Okay, so this just allows you to do induction. So you can do induction on a well-ordered set, basically. And so we won't go too much into the, I try to make it kind of simple here because the details are kind of technical, but what you do is, okay, we've got our arbitrary product of compact sets. So let's do the standard thing. Let's assume we have a finite cover which doesn't have a subcover. And let's try to get a contradiction. And so what you use instead is you use a form of the tube lemma, which says that if you're given an open cover of X cross Y with X compact, right? So Y doesn't have to be compact. If there is no finite subcover of the whole space, then we can find an X in our compact space X such that that slice X cross Y doesn't have a finite subcover. And so then the basic idea is you find these spaces, subspaces, where this is a point, and then these are, so we're using the well ordering, right? So such that for everything before, everything up to alpha, we've just got a point, and afterwards we've just got our our subspaces, that has no finite subcover. And then we do our inductive set where we can find such a subset with beta greater than alpha having no finite subcover. So then by Trans-Finite induction, the last set you get is just going to be a point, but it's ridiculous to say that a point you have no finite subcover. And that's a contradiction. And it's a very unsatisfactory proof. Because it's using the well ordering, and I don't know, it just feels like you're cheating. And as well, there's a lot of technical details here. Mainly, but the reason why this works is because we're in the product topology. And that's the details that I've kind of left out, right? Because it's only true in the product topology that you can do this. So, and this is not really how Tychonoff's theorem is proved by people. People just think that it's too unsatisfactory. And so we're going to abandon the idea of doing open covers, and we're going to use the closed subspace criteria for compactness instead. And that's where Zorn's limit comes in. Okay, so just remember what the closed subset criterion is, that if you have a collection of subsets of a space, it's said to have the finite intersection properties, or fit, if for every finite subcollection, the intersection is non-empty. And the theorem that we proved before, that if you've got a topological space, then X is compact if and only if for every collection having that finite intersection property, the intersection of all elements is non-empty. Okay. So that's what we want to work with. Okay, so let's try first to do a proof for the case that we already got. You know, like when we've got a product of two subspaces, how are we going to use finite intersection property to prove the space is compact? So let's start with naive proof. It's naive because obviously we're going to fall flat on our face at some point. But Zorn's lemma is going to say this. Okay. So we want to show that the product of two compact spaces is compact using that finite intersection property. Okay, so let's say we have a collection of closed subsets having that finite intersection property. Now, if we just look at the projection onto X1, that has finite intersection property, as does their closures. So we can find an X1 from that intersection of projections. Similarly, we can get an X2 from the intersections of the projections onto X2. And the question is, does X1 cross X2 going to be in the intersections? And if you just think about it for a moment, you're going to say no. And here's a quite easy example. So our X1 and X2 is just going to be the unit interval. So, we've got the unit square. And we're going to let A be the collection of closed elliptical regions bounded by ellipses with foci at 1/3, 1/3, and 1/2, 2/3. Okay, so here are the foci here, and we're just looking at all the ellipses that we can fit into the unit square that. So that definitely has finite intersection property, right? Because it has to contain the two foci for a start. So what actually is going to be the intersection of all those ellipses is just going to be that really just the segment joining those two focal points. Because anything outside of that, you can get an ellipse which is so eccentric, it's going to, you can basically get as close as you like to that red line. So any point of that can't be in any intersection. So that's what you want to pick up points on that red line. But the problem is, if we use the naive approach, we're actually just going to do things from the blue region, right? Because where is it? A third, a half down here. That's all. They're all candidates for our x1, and between 1/3 and 2/3, that's all candidates for our x2. So anything in the blue could be chosen, but we're only going to win the game if we choose the red. So, for example, we could have chosen a half, and we lose. So we've got to fix this. So how do we fix it? So what's the problem? The problem is we've got too much choice, right? We were allowed to make a wrong choice here. So how can we force ourselves to make the right choice? Actually, it's not going to be more specific, it's going to be bigger, right? Because if you take a bigger collection, intersections go down with the size of the collection. So if you're intersecting a lot more things, that's going to make your choices more restricted. So, for example, so what we want to do is actually expand the collection A, but we still want that finite intersection property. And the reason why, again, is because more things lead to smaller intersections, so there's less choices that can go wrong. So let's go back to our example. So instead of A, the collection of ellipses with focus at 2 points, instead we'll let C be the collection of closed elliptical regions bounded over ellipses with foci at 1/3, 1/3, and R just any point on this line segment here. Right, so C contains A, right, because it includes those points that focus here, but it's also, so we've made our set a whole lot bigger, but only choice for x1, if we look at all the projections of our ellipses, is going to be the point 1/3, and the only choice for x2 in the closure of the intersection of all the points projected onto x2 is 1/3, and so we get 1/3, 1/3. We were forced to choose 1/3, 1/3, and that is in the right place. Okay, so that's the motive for what we're going to motivate what comes next. So how do we choose our set D, our collection to be? Well, we choose D as large as possible. Okay? So we want it as large as possible, but still to have the finite intersection property. So that's a maximal object, so that's Zorn's lemma right there. So Zorn's lemma is going to enable us to prove that there exists the correct collection. The other thing was, notice we never used closure, as you know, we never used the closure of the sets there in the proof, because if a set is closed, then its projection doesn't have to be closed. So what we're going to do is we're going to look at arbitrary collection of subsets with finite intersection property and prove that the intersection of their closures is non-empty. So that'll make the proof a little bit easier. Okay. So we want to prove that there exists a collection maximal with respect to the finite intersection property. So basically this just says there exists the right collection. So we have a set, we have a collection of subsets of X having the finite intersection property. We don't want to look at that collection. What we want to do is increase it A to D, which is the collection of subsets of X containing A such that it has finite intersection property, and no collection of subsets of X that properly contains D has this property. So it's the biggest with respect to that property. So we need some notation. So we're going to let lowercase letters be elements of X, uppercase elements be subsets of X, script letters be collections of subsets of X, and blackboard bold letters be supersets, collections of subsets. Because this is where we're going to apply Zorn's lemma to. Okay, so we're given our collection of subsets of X having finite intersection property, as we have it from our hypothesis of our lemma. Okay, so we're going to let boldface A be the superset of all collections of subsets of X containing A and still has it. And we're going to use proper inclusion as the strict partial order. And so what we've got to do to be able to use Zorn's lemma, we've just got to show that subcollections in this blackboard bold A have an upper bounds. Once it has an upper bound, then it has a maximal element. And that maximal element, of course, is our desired D. And that's not really that hard. So let B be a subcollection of A. We want to find an upper bound for it. Well, it's simply ordered by inclusion, so the obvious upper bound is just the union of all the elements of B. That's how all these proofs go, and it always works. So what are we going to do? We've got to show. We've got to show that this upper bound, we've got to show that it lies in A. And the definition of A is it's the collection of all. It's got to contain curly A, and it's got to have finite intersection property. So those are the two things. Well, since each thing in the subcollection contains A, then C, being the union of everything in B, also has to contain A. So that's free. So the only thing we really got to think about is finite intersection property. But that's not hard either, right? Because if we've got elements in our upper bound, C1 through Cn, then we know that for each Ci, there's a BI such that CI is in BI. So instead of this collection, we now, instead of the collections of the C's, we should look at the collections of the B's. But the B's are simply ordered, right? It's a chain by inclusion. So therefore, there has to be a largest element. Let's call it VK. That means that C1 through Cn have to be in VK. And since VK has finite intersection property, that means the intersection of C1 through Cn is not empty. That's all we need. Our upper bound has finite intersection properties, and therefore it's in our set A that we wanted. C is an upper bound for B, so therefore, by Zorn's lemma, A has maximal elements, and we're going to let that D be that maximal element. So it looks very abstract nonsensy, but it's actually pretty straightforward. All you got to do, it's just like mastering the notation, really. I love the fact that you need 4 different types of symbols to express it, but it's the obvious thing, right? Just keep using it for everything. Okay, so now we've got that lemma. We need another lemma as well, and so we've got our maximal element D, and so we want that maximal element to have some various properties that we need for the proof. Okay, so we've got D, a maximal object with respect to finite intersection property. Then any finite intersection of elements of D is also going to be in D. And if A is any subset of X that intersects every element of D, then A is an element of D. And this is not hard at all. We just use the maximality of D. Okay, so if we take some finite collection of elements of D and intersect it, let's call that D. And then we're going to define a new set, collection E, to be D union B. If E has a finite intersection property, then E has to equal D because of the maximality of maximum. Because D is maximal, and so therefore B has to be in D. And that's not hard at all. We just take a finite intersection of elements of E. Now, if none of those elements is B, then the intersection takes part in D, takes place in D, which has the finite intersection property. So therefore, the intersection is non-empty. If B is one of the elements, then the intersection looks like D1 through Dn, where these are elements of D and B. But B itself is just a finite intersection of elements of D. So this is still just a finite intersection of elements of D. And so since D has the finite intersection property, it has a non-empty intersection. Hence, E has pip. So E is D. The second one looks almost the same. Given A, again, we define an E as D union, just adding A to the collection D. And again, we just show that this has a finite intersection property. Okay, so again, we take a finite intersection of the elements of E. If none of those elements is A, then the intersection takes placed solely in D, so the intersection is non-empty. Otherwise, the intersection looks like intersection of D's and A. But D1 intersected through Dn belongs to D by part 1. And by the hypothesis, A intersects every element of D, so therefore this intersection is non-empty. Again, E has finite intersection property, so E equals D by the maximality of D, and A is empty. So that's just a nice logic set theory, really, but not too hard. Oops. Tychonoff, I put in the wrong dates there. The date is actually 1930 and 1935. So in 1930, he proved it for the case where X is the unit interval. And in 1935, he proved it for arbitrary compact spaces. And actually, the 1935 paper is where he defines the product topology. So basically, he found which topology arbitrary products of compact spaces is compact, and he used that as his definition for the product topology, and that's been what's been used ever since.
Are you saying the 1930 paper was the last topology?
Well, he was just looking at the cube. Like he was just in 1930. He was just looking at right. No. But in the product again, he used the product topology, but he didn't define what the product topology was. So it wasn't until 1935 that he proved everything in general, and he put everything in context and said this is the right topology then to use for products. I feel like I'm going really fast. Are you okay? Okay, because it's not, yeah. Okay. So, again, let's take a collection of subsets of X having the finite intersection property, and we just want to show that the intersection is non-empty. Okay, so we use lemma 37.1 and we replace A by D. The collection of subsets of X such that D contains A and D is maximal with respect to finite intersection property. And by the way, that's exactly what we did when we looked at the case example with the ellipses. We took our A and we replaced it with a bigger question. And notice there were different ways that we could have done that. You know, we could have used the other focus, for example. Okay. So, for each alpha in J, we've got a collection of subsets of X alpha, which is just the projection onto X alpha of elements of D. Okay, and this has finite intersection property because D has a finite intersection. So that means that each coordinate there has to exist something. Now, since we're in X alpha is a compact space. Therefore, since this has finite intersection property, there exists an X alpha, which is in the intersection of all the closures of those projections of those subspaces. Okay, so that's an X alpha. And so we're going to let X, this vector here, just then be the tuple that consists of all those X alphas. So then going back to that example that we did, that was kind of what we had. Okay, so we've got to make sure it works. Okay. Well, for each X beta chosen, I don't know why somebody switched from beta to alpha to beta. So for each coordinate in one of our coordinate spaces, let's say we have a neighborhood. U beta. Okay. So since X beta is in this closure here, okay, because this is how we define X beta, we have to have that this neighborhood intersects this interior, the pi beta of D. At some y. And so if we do that for all the beta in J, we end up with a y in D. And so we have this sub-basis element intersecting every element of D. And so by now we can go back to lemma 37.2 and say, since that intersects every sub-element of D, it itself must be an element of D. So every sub-basis element containing X belongs to D. And since D has that finite intersection property, every basis element containing X intersects every element of D. And so that means X is in the closure of D for every D in our collection. So since it's in every D, therefore that shows that the intersection of all the closures of D's is non-empty. So that means the intersections of all the closures of A is non-empty. And so that means X is compact.
So why don't we clean up the subbases?
Well, I mean, this is what a sub-basis element is. I mean, we've taken a neighborhood in here, and then we've just looked at its inverse image in X. And so, I mean, that's just what a sub-basis element is. I mean, we're just starting from a neighborhood here.
So then how do you make the jump to the basis? I don't understand that.
Hence, by fixing every sub-basis element containing X belongs to D. So how do you get basis elements from sub-basis elements? You take finite intersections, right? And so since D has that finite intersection property, you can go, this tells you that you can go to basis elements. And so since this is true for every basis element, it's true for every open set. X. So therefore X is in the closure of D. Right, because we want to show that any neighborhood of X intersects every element of D. But if it's true for basis element, then it's true for open sets.
Right.
And so that's why we needed sub-basis elements, because we can go from sub-basis to basis just by taking finite intersections. So I kind of think the proof is pretty neat. So actually, you know, Tychonoff's theorem is actually equivalent to axiom of choice. Just like, you know, every vector space having a basis. So it's just one of those theorems. But firstly, it's a theorem that's used a lot in because compact spaces are so useful, they have such like useful properties. Quite often you want to prove that something is compact. And supposedly Tychonoff's theorem is just like kind of like a workhorse for proving that things are compact.
Is there a specific reason we didn't assume that script A was a collection of closed subsets? I guess at the end you have the intersection of the closures. That would be
right. So if they were closed,
the same thing. Yeah. Was there a specific reason for that?
right, because there was no need for A to be closed. Because quite often when you have a projection of, remember,
Right.
you saw a
Right. I understand you still have to bring up the closure in the middle of the argument. I don't know. I just thought it was a little confusing to have the intersection of the closures with the element, but it's not a big deal. The intersection of the closures with A.
Right. I guess, but I mean, as I say, if A is closed, then it's the same thing. So it's just slightly, I guess it's slightly more general, so that's why they move it in.
Okay.
Okay, I'm sorry. I think I might have gone a bit too fast, but anyway. It is. When I talk to other people who talk topology, they say they never do Tychonoff's theorem. What? It's so important.
Yeah. In all honesty, I would have been satisfied if we just assumed numbers or something and just talked about the topology part. In all honesty, but I'm not that.
Well, the second lemma I thought was kind of neat because I thought it was kind of you know, when you're doing those intersections and the fact that you're using maximality, I thought that was kind of neat. The first lemma, you know, was okay. It was just like super complicated, just because you have to tie yourself in a knot with collections and collections and collections. Yeah. So I think next week, I have to go to Chicago to get my passport. So I think I'll cancel Friday's class. But that should be okay because we have Thursday off as well. So Monday and Wednesday, at some point, I've got to give back more homeworks. And I want to talk about the stone check application. And so that just leaves the last week. And so the last week, we can either do chapter 7 or chapter. Look at the thing here. So we can either do the complete metric spaces and space-filling curve or VS spaces, and we've sort of got a choice out of one of those two.
No word differentiable.
Do you want that one?
Yes.
Okay. Okay, so we'll do that then. And that'll be it.
Can I ask one question about the homework?
Sure.
When I the compact house one, suppose that so it's kind of like a manifold, except they don't have to all be associated with the same primary thing, right?
Right.
And then show that it can be embedded like a single.
So yeah, so for example, you might have, I guess you might have something like a lollipop or something.
Right. Right. You get the one-dimensional portion. How do you even how do you get a hold of that assumption though? Like, I just don't understand how to work with that.
Can't you just do the, I thought it was just like redoing the proof a little bit.
Produce a coefficient of unity somehow.
I think so. Let me write. Oh, can you just send me an email?
Okay.
About that, and I can certainly send you something back. Oops, I meant to stop recording.